No, I have so many.
There's 3 samples, right? So we ran 3 different samples. So yeah, that was all.
So you get to what is the range of the intensity that you want?
Well, I don't really know about that. So we did
What is it?
1-to-1, 1-to-30, 1-to-10. We did a 1-to-1, 24.
What's a 1 to 99? What's it like?
For the chlorine,
Okay.
for the iron peaks. So the ones 24, or the ones have a good probably have the sulfate and then there's
He said right 2 to 3 hours. The one you said, the one you said the fluorine. No, I didn't. I want to it says like 2 to 3 like that.
yeah, there's only so if there were less chlorine,
All right, let's go. So today we're going to talk some more about chromatography, and I want to. So you have 2 more labs left to complete the lab number 2, and I want to provide the time so we provide enough of the background about chromatography to be completed with that, probably by part of the lecture on Wednesday, so that when you finish the lab on Thursday and start preparing for the next lab report, which will be before Thursday, you'll have enough of the background to know how to structure things. So we're going to talk a little bit about the suppressor function today, a little bit about detectors and the ion exchange that you're using, and probably on next Wednesday I'll talk about what kinds of detectors and other chromatographic applications. And then I want to kind of go over some of the different types of chromatography that are commonly used. Ion exchange that you're using in lab is less commonly used than most. Probably the most commonly used form of liquid chromatography is reverse phase. We'll talk about the different normal and reverse phases, ion exchange, size exclusion chromatography, because all these are commonly used in labs across chemistry and biological sciences. And then I'm going to take a little time at the end to talk about lab reports. You guys all got the reports, right? You looked them over, and I sent an email out. I think everybody got saying that there are people here who want to try to come by around 4 o'clock. Raise your hand if this is true. So I'm there. So I can kind of go over some of the comments with you. But I'll take about 10 minutes at the end today to kind of look back and talk about lab reports and what, how best for you to move forward in revisions to do the best possible job in your revision. Okay. Okay. So this is, you're familiar with this now. You've been using it for a day and a half, or roughly so, and I know that that both Vince and Taylor went over the various components, and we talked about it a little bit in class, right? And the one thing I want to talk about today is the suppressor, because it plays such an important role in the function of ion chromatography. And so I'm not going to go over this. We talked about that. We talked a little bit about this, but the columns you're using, how that's working. What I want to start with here is thinking about the ion suppressing system that comes in that particular instruments you're using. So to start that, first, what is the buffer system, the mobile phase that you guys are using in this, in your separations?
Carbonate.
What is it?
Carbonate.
Okay. And so what does that look like?
H2CO3.
Okay, so we have, start this way. Okay, so you all know that carbonic acid is a weak acid, right? What's the pKa of this reaction? Anybody remember approximately? Don't be shy. Okay, no, the pK. A weak acid. Right? So, as a weak acid, you know it has to be less than this, less than 7. Right? 6. Okay. What does that mean? The pK is about 6.3 for this first association reaction.
Negative log,
Okay, and what does that mean? The negative log of K, so the Ka is 10 to the minus 6.3, right? What does that mean? The reaction, right? What is it? You see something? That's true. That's right. But in terms of this value, remember in chemistry you learned that at a pH equivalent to the pKa, that you have equal distribution of the two forms of the compound, right? And so at a pH of 6.3 for a dissociation like this, an association with the pKa of 6.3, half of it is dissociated and half of it is associated, right? And at a pH less than 6.3, what happens? You get more of this, right? Because there's more protons. At pH above pK, you get more dissociation, right? And so, why are you using this buffer? Because you want to talk a tiny bit about this in the laboratory. Why are we using a carbonate bicarbonate buffer system in the mobile phase? This is to get us thinking about why do we have an ion suppressor in our instrument?
Is it to keep our stationary phase with a positive charge on it?
Okay, so we know we're doing chromatography, and we know that we have a column, and what is the functional group in our column?
It's a tertiary ammonium sulfur.
Right. Did you say tertiary ammonium?
Yeah.
Yeah. Okay. So we have this NH3 plus essentially in that column, right? And we're trying to separate anions, right, that are coming through here. Okay. So what's the pH of the mobile phase we're using? Okay. You want to know this, right? Because this is like when even though you're using it because somebody made it, it's important that it be known what it is, because if it was something different than what it's supposed to be, it would be a big problem. So the pH of the mobile phase is probably around 6, roughly around 6, right? And what that does for us, it tells us that we have a distribution of the buffer into these two forms, right? So we have a fair amount of it in the dissociated form of bicarbonate. And so now we have this ion exchange interaction going on in our column between the anions we're trying to separate that have different degrees of electrostatic interaction with the tertiary ammonium on the column, right? And we have been bathing those anions bicarbonate, right? So now we have a lot of bicarbonate in there that's competing with these anions that we want to separate for electrostatic interactions with the tertiary ammonium on the column. Right? And so we have set up in this column this very dynamic battle competition between all these bicarbonate anions, and the anions we're trying to separate. And we're relying on the fact that there's a relationship between the amount of this, the amount of these, and the relative affinity, electrostatic affinity for interactions with quaternary ammonium to determine who partitions here and who stays in the mobile phase. And that's what determines our separation. So we have this very important system here where we choose this mobile phase to do this. If we just use water in this mobile phase, we'd be washing our anions over there, they'd stick to this, and they'd never come out. They'd never come out of the column. And so it's this very important competition that actually helps facilitate the degree of partition that they exercise with the stationary phase. Allows it to separate the anions that have different partition coefficients with the stationary phase. Okay? That makes sense? We haven't talked about this yet. So now we have this, and we have a fair amount of this in the buffer system that we want. So we're using this weak acid buffer to do two things. One, maintain a pH, so we don't get this wildly changing pH or changes in the mobile phase composition as we're eluting our samples, which would change the elution profiles. So we're maintaining a constant pH in our elution, and we're providing a relatively high concentration of background anions that have weak affinity for the functional group on the column that our anions of interest are competing with. And if you look at the electronegativity of some of the anions that we're separating, that you're separating, like chloride, maybe fluoride, and so on, obviously they have a much higher electronegativity than do bicarbonate. That's why they have a higher electrostatic attraction to the quaternary moment. So we have the chemistry going on in here, and now comes the issue with the suppressor. So let's pretend that this is our detector. I'll talk about that more in a minute. And our detector is essentially a very thin cell, meaning it's a very low volume, that our eluate is passing through. And in the detector, we're trying to conduct a charge, a current, across the detector, and that conductance of trying to pass a current across that space, that liquid space that's filled by our eluate, that conductance is what we're measuring as the signal. And so the more anions, whether they be positive or negative, the ions in this solution are going to affect the extent to which a current can be conducted across that cell volume. And I'll talk about that more. So here is the conundrum. We have a buffer system that we need in order to maintain pH and to provide an environment within the mobile phase which is going to set up the competition between our anions of interest and the functional group in the column, the stationary phase. And so we need this in there to maintain the pH and set up that competition to facilitate the different partitions of our anions. But we're using a bulk detection method that's measuring conductance that would be swamped by the concentration of this anion in our mobile phase. And so if we didn't have a suppressor, and we'll talk about how that works, we would be unable to make the kinds of measurements we're making. So if you look at this cartoon up here, this figure, this is just sort of a cartoon of what the instrument looks like. And there's one very important thing I'm going to point out. One is that we have our column where the separation is occurring in the presence of our buffer, and the very important role that the bicarbonate in your case plays. In other cases, it could be potassium hydroxide, could be the buffer system. Right? In your case, it's sodium bicarbonate. So we have the column where all the chemistry is happening to separate our anions, and then comes the suppressor after the column, right? Because we've separated everything we want to separate in the presence of the buffer system. And now we have to deal with this high concentration of an anion so we can actually measure our anions of interest. And if you look at this chromatogram here, if you turn the suppressor off, which you can do quite easily on the IC, if you turn the suppressor off, you would see a baseline that would just jump off the screen on the computer screen of your instrument, because you'd be measuring a very high conductance because you're measuring the conductance with the bicarbonate ion. And then you turn the suppressor on, and then the baseline drops down to where it is after it's stabilized as when you're using it, like this, because the suppressor is actually removing that bicarbonate ion, but not a contribution to the conductance, but not altering the conductance due to your anions that you're separating. And that's the magic that we talk about. So this is what it would look like with the baseline way up here. You barely see the tops of your anion peaks that you care about. And here's in the presence of the suppressor on, that it drops that baseline due to the bicarbonate conductance, and now you can really see the conductance due to the anions of interest. And so for a sensitivity standpoint, it increases the sensitivity of the measurements that you're making by over an order of magnitude. So you're able to measure concentrations of anions of interest at levels that are at least tenfold or more lower than what you'd be able to measure if it didn't have a suppressor. And the question is, how does it do that? And that's what we'll talk about. So this is what the suppressor looks like in your instrument, and this is kind of how it works. You have the suppressor, and this is important, it always appears after the column, after the separations have occurred. Okay? It can't happen before, otherwise you'd get no separations because it would remove the bicarbonate. So you have the eluate coming right out of your column through that really skinny tubing that has an ID, an inner diameter of probably about 0.007 inches. I'm not sure what it is exactly in the tubing years, but it's a very, very small inner diameter of that tubing that exits your column. And that small diameter helps keeps things from diffusing, helps keep the analytes that have been separated from diffusing and the peak broadening it, which would reduce your chromatographic efficiency. So that eluate from the column comes out of the column and enters directly into the suppressor. And the suppressor in that little device is comprised of a number of different membranes that are semi-permeable. So on one side there's an anode, on the other side there's a cathode, and a potential is being applied to the anode relative to this cation exchange membrane. So you see this is positive, this is negative, and over in the cathode this is negative, right? So these are both two cation exchange membranes. Your solution from the column is coming through rich in bicarbonate, as well as the anions that you're trying to separate, which aren't shown here. Okay? And you're using a sodium bicarbonate. So you have the bicarbonate as well as the counterion. The cations come in as part of your eluate, right? On the anode, in this space, on this side of the cation exchange membrane, the potential is oxidizing water against this anode and oxidizing the water into oxygen and protons. And if you look closely at the tube coming out of the suppressor in the instrument, there's a tube that's taking the regenerating solution from the suppressor that's recycling it. And if you look closely at it, you see a lot of air bubbles in there. And those air bubbles are the oxygen that's being formed by the oxidation of water at this anode. So in producing all the oxygen and then all the protons, which matter, the protons are able then to diffuse across, from a high concentration to low, diffuse across this cation-specific permeable membranes into the eluent space where your column eluent is going. Those protons then combine with the bicarbonate to form carbonic acid, which is no longer conducting. Okay. The sodium cations are able to diffuse across the membrane, because they're also ions that would contribute to the conductance in the detector, diffuse across the cation permeable membrane, and essentially into this regenerated space. They're being drawn by electrostatic attraction to the high hydroxyl anions in here. They diffuse across into this space, and they're essentially flushed out and it regenerates itself. So in this process, you have all your anions coming through, including a high concentration of bicarbonate, and the bicarbonate is then combining with a relatively high concentration of protons that are diffusing and immediately reacting at this surface with the bicarbonate to form carbonic acid. And it's non-conducting, and the sodium is diffusing out. So you're depleting this space of the interfering anion and the high interfering cations before it flows out and into the detector. And so when you turn the suppressor on and off, all that's doing is providing the potential to the anode and the cathode to start this electrolysis.
And this is happening along the column? Or
This is happening
after the column?
after the column. So if you look at your instrument, this is it right here, right? And so the tubing, you can't tell from this, let's say, but you know, you inject your sample, it goes through the sample loop, and then it goes and winds the tubing, it goes through your column, the guard column, which is over here, I think, or here, I can't remember what you can tell where it is. It looks just like maybe it's shown here, but it really, in yours it's over here, I think. It goes through all that, and then it enters the suppressor, which is this. And then after the suppressor comes out, it enters the detector. So it's a nice bit of chemistry that allows us to increase, the sensitivity by at least an order of magnitude in measuring the anions. Right? And it works basically the same way, whether it's a carbonate bicarbonate buffer system that you're using, or whether it's a potassium hydroxide different kind of buffer system.
Why does this not remove other anions from the lab base?
Wow. It's a good question. Why isn't it removing other anions from the LU1 coming out of the column?
Because did the anion bind with the mobile phase already?
Did it again?
So when you go through the column, did the anions bind to the mobile phase?
When you go through the column, do the anions... So the anions are in the mobile phase.
Yeah.
So I'm not sure I follow you. So
Just kidding.
okay. So why? Well, but that's an important thing. Why is it that you are not altering the levels of other anions in there?
Aren't most of them not really all that basic?
Because they don't have the same pKa that the carbonate bicarbonate does, right? And so by having this solution with a pH of about 6, you have a fair amount of this that can react quite readily with even the slightest increase in protons, and it's going to shift it that way. Right? And so it's because that you are operating this buffer system at a pH that's around its pKa. It's a very sensitive buffer system to any change in this, which is what you're providing. Right? But the other anions, if you were to substitute this for chloride or fluoride or sulfate or whatever, they're not so reactive with those protons, and they certainly won't form, they're not function as a weak acid or a weak or a base. So they're not reacting. That's why. Okay. Does that make sense? You guys got that? Because we're gonna ask you in your report to talk briefly about the suppressor and what role it plays. One thing for lab report number 2 and number 3 that you're going to expand upon from the first one is a much more developed discussion of the instrumentation, the theory of the instrumentation, and how the different components work that are essential for the function of that method. And the suppressor, in this case, for plate exchange is one of those. One example of that. Okay, so the detector on this is like we talked, is measuring conductance, right? And conductance is essentially just the movement of electrons from one side, one pole of the detector, one side of the volume of that cell to the other. And of course, things that have higher conductance would be analogous to things having higher concentrations of dissolved ions in the solution in which to conduct that current from one side of the cell to the other. And so the problem with these detectors, and the reason that a suppressor is needed, is that they're considered to be bulk detectors. And bulk means that it's measuring the bulk conductance of a current across those poles in the detector, and it's not specific for any particular anion or anything. It's just basically measuring the extent to which that solution can conduct, this passive group can conduct a current across. Right? That's what and when we think about conductance, there's two things that we have to consider. One is whether the current is going to pass across the pole, conductance, or whether it's not. Of course, that's resistance, right? And in direct current electrical circuits, we talk about resistance, and resistance, of course, is the inverse of conductance, right? But in alternating current electrical circuits, like we have here, it's plugged into the wall, right? These are AC circuits. It's not resistance that really is determining the conductance. It's actually impedance. So resistance is applicable in direct current circuits, and impedance is applicable in alternating current circuits. Right? And the reason that they, aside from that we all have AC currents coming out of our walls, the reason that this doesn't have a transformer to convert the AC to DC is because in conductance detectors that are operated under a DC current circuit, over time there's a polarization of the poles, and then there's a drift in the baseline that becomes noisier. So it's not as effective as a electrical circuit controlling conductance detectors if they're direct current circuits that are wired into compared to their alternating current circuits. So all that matters for us then is thinking that I have two processes that are essentially at play here. I'm measuring conductance with my detector, but what is determining conductance is really the amount of impedance or resistance to the passage of current from one indication to the other. Okay, does that make sense? And you could think of it like a river, and the river is the conductance, the movement of the water, and the river is the conductance. But what determines how much water can move down the river are the things that are in the way of the water moving, whether it's the debris in a river or a dam in the river. And so those are things that are providing impedance to the flow of the water, of the current, just like a circuit like this. So in your solutions, the absence of ions is what is providing the impedance. Because water itself is not a very good conductor compared to water that has dissolved ions in it. And I say on this there, so we'll roll that. All right, so now if we look at this whole system put together in sort of a cartoon form, we know that if you were to draw this, we know how you start with your eluent that has certain concentrations of a buffer system that you are now very familiar with, and will become even more familiar. That buffer eluent is pumped through a series of 2 pumps that are very effective at pumping without any pump oscillation and under relatively high pressure. And they go through a sample loop in which you've loaded your sample, in which case it's 25 microliters. These are details that you want to make sure you make note of because that determines how much sample is going on the column, obviously, right? If you wanted more sensitivity, you could, in principle, change that out, and we have multiple sample loops, and put in a 50 microliter sample loop or a 100 microliter sample loop. Yours is a 25 microliter sample loop. And then it goes to the guard column, and the guard column we talked is the same material as the analytical column that you're using, but it's much smaller. And the idea is it's not necessarily supposed to facilitate separations, but it's supposed to help protect the analytical column from the inadvertent injection of samples that have high concentrations of particulates or things that may clog the analytical column. And the cost of the guard columns are relatively inexpensive compared to the cost of the analytical column. And then it goes to the analytical column, and then it goes to the suppressor we've talked about, where you remove the influence, the conducting influence of the bicarbonate and sodium ions. Then it hits the conductivity detector, and then you get your chromatogram on this computer. So you'd be able to put all these components together and understand what roles each of those are playing and which ones are you will have control over in terms of selecting as an analyst.
What's the guard column?
What
is the guard column?
It is packed with the same material that's in the analytical column. And so, so it's packed with a stationary phase that has quaternary ammonium functional groups on it.
So why is that much cheaper?
Because it's really tiny. It's small. It's about this big, and then the analytical column is about that big. And for the guard columns, you typically, they fit in, a lot of times they fit in a little housing, and it's like buying a little cartridge. You can unscrew it and put it in, and change them out pretty easily.
Do you have to keep that in mind when we calculate use the length of the column to calculate?
No, because the guard column doesn't really facilitate separation.
Why doesn't it separate out the anion has a quaternary ammonium?
Because it's so small. It's just small. That's why. So it's meant to kind of be there, not to change anything. That's why it always meant for guard column, you should always match the stationary phase of your analytical column, match that in the guard column so that you're not have competing kinds of processes. But it's so small that not much can happen over that space before the sample is through. And not all systems have guard columns, only the ones that, that the people that are smart that have learned the hard way that it's expensive to replace that analytical column. All right. So I mentioned before, I said, there's a lot of applications that different companies develop, and their bread and butter in developing applications is developing columns to meet certain applications. And sometimes people from this class go into environmental consulting kinds of positions within environmental consulting companies, where they do a lot of analyses of environmental samples, samples from wastewater, effluents, a whole variety of things they have, where there's a lot of monitoring that's required because of EPA regulations and so on. And so companies like Dynex and Waters and others, they actually have a business where they have labs of research staff who spend their days developing analytical methods to be able to separate and measure things with increasing sensitivity and specificity to be able to utilize in these industries that are sort of doing all this water monitoring or whatever they're monitoring as part of some government regulation. And this is just a web page, it's probably a year or two ago, but this is just a web page, part of it, of looking through. And each of these are application notes for different kinds of methods. Direct determination of fluoroacetate water by CEMS, sensitive online SVE, HPLC, determination of paraquat, diquat, drinking environmental waters. So they actually spend time developing these methods, testing things, changing the parameters of their chromatographic methods in order to optimize applications, and then they write these up in these nice little method papers, and they post them so that people like you or me who are doing this could then adopt one of these methods in the job that I have to measure these samples. And the advantage is, of course, it's a two-way street. The advantage is that they're doing a lot of the R&D for us in the industry, and of course, all these methods are based on Dynex columns. And so we'd buy their column. And the one caveat with chromatographic methods is that they're really specific to the column, because all the action happens to the column, and there's a lot of chemistry and black magic that happens there that sometimes can't be easily explained by chemical theory. And so some of these methods are developed empirically, meaning that try this and modify this, and we modify the mobile phase and a number of things to facilitate a very specific kind of application of separating specific kinds of compounds. And so the end result of that is that, buying a column from Dynex with a quaternary ammonium group to do a particular separation will oftentimes work differently than if I bought a similar kind of quaternary ammonium column from another manufacturer, because they're all slightly different. And so there's a great niche in developing these kinds of methods, and there are pages and pages of these kinds of applications that these companies publish. There's, I think, tremendous benefit. Okay, so now let's back up a little bit. If we think of liquid chromatography, and the methods we were just looking at from Dynex, that's not, of course, just applying to ion chromatography. That's across all different kinds of chromatography. And so I think we want to get a clear idea of these different forms and how they're used and what the basic separation processes are, because this is kind of what drives what we might start thinking about if we headed to adopt a methodology. You graduate here in June or whatever, and a lot of times, like I said, students get jobs out of school with laboratory experience like this in some kind of analytical chemistry lab in the private sector. And a lot of times they join a lab and they're tasked with modifying or developing a method to measure something in some kinds of samples. And oftentimes that involves some kind of chromatographic method. And so the first step is trying to get a sense of what is it I'm trying to separate and analyze, and what are the chemical properties of those compounds that I'm trying to separate and analyze. And then based on what I know about their chemical properties, I can then start selecting what might be the most appropriate chromatographic approach. And so chromatography is all based on, and we've talked about this a lot, chromatography is all based on a column, and it's based on the interactions of the stationary phase with the interactions of analytes, inside the mobile phase, right? And it's this interaction that is facilitating the separation of this analyte from some other analyte in that column, which is our whole point, right? And so if you know the chemical character of your analytes that you're trying to separate, then you can select what might be the most appropriate chromatographic approach. And so there's probably 4 or 5 different primary methodologies using chromatography based on the kind of chemistry that's occurring in the column between the mobile phase and the stationary phase. And I'm going to go over those quickly, what they are.
In all cases, of course, the column is a tube, and it's packed with beads, typically, very tightly, that have functional groups on those beads that impart certain chemical characteristics to that stationary phase. So in the case of normal phase chromatography, what that's talking about is that you have two basic kinds of processes that are driving separations, right? And one of the most basic chemical parameters or characteristics of the chemical that's used to separate is whether it's polar or not polar. And so normal phase and then reversed phase chromatography is all talking about the polarity of the stationary phase relative to the polarity of the normal phase. And so in normal phase, the stationary phase is polar, and the mobile phase is the opposite, non-polar. And now, depending on what the chemical characteristic of the molecule is, it'll partition more strongly in one or the other. You would vary these parameters of mobile phase to sort of select that interaction. With reverse phase, it's just reversed. Where the stationary phase is nonpolar, like a carbon chain, and the mobile phase has polar characteristics. Very simple, right, in that sense. It's very complicated how things behave in there, but the basic of it is just as simple as that. Let's see that there. Size exclusion is a very common method. In size exclusion, just like the term suggests, is separating analytes based on their size, right? Based on their size. And how does it do that? Size exclusion is typically done where you have these porous beads, kind of like a wiffle ball. Does everybody know what a wiffle ball is? Yeah? When you're like, whatever, 10 or something. Okay, and so this column is packed with these wiffle balls. Of course they're not. They're really tiny beads that are hollow. And these beads have different diameters of pores in them. And you buy this size exclusion gel or beads depending on what pore size you're looking for, right? And so you have a column that's packed full of these things, these wiffle balls, with a pore size that's selective for a particular molecular weight size based on what your separation is. And so let's say you're trying to separate things these are for larger things. These aren't for dissolved small compounds. These are for things usually in the 2,000, maybe up to 100,000 daltons, right? Molecular weight. So these are biological molecules typically that you're trying to separate, not small anions or things. And so you can have a range of maybe 2,000 to 10,000 for the mean diameter of this pore. Maybe from 10,000 to 30,000, maybe from 30,000 to 60, so there's different size ranges of the pore diameter, average pore diameter in these beads that are packed in the column. And then you load your sample on, and I'll draw one that's bigger now, just so you can see it. You load your sample on, and the things that are small, smaller than the pore size of these beads, these wiffle balls, will travel through and get inside those pores and finally come out, because there's a net flow this way. And so their path through the column, if you're small, is going to be a lot longer because you're spending a lot of time inside these balls. Right? And if you're bigger than this pore size, you're not going to go in there. You're just going to go on the outside of all those balls, and your path ultimately will be shorter. So when you look at a chromatogram from a size exclusion column, the things that come out first are the big things, and the things that come out last are the small things, because they spent longer in the column in those balls, right? And so the relationship between when you elute is directly proportional to your mean diameter molecular size, right? And there's a relationship between molecular weight and size, and that's what determines whether you go in and how often you go in, probability, right? And so size exclusion is simply doing that. It's excluding, eluting analytes or molecules based on their size. Okay. And I've already asked you on a quiz, in size exclusion, who comes out where? You say, well, the bigger guys come out first because they don't get these balls, they spend less time that they're going around, and they come out first. The little ones are all trapped inside of it as they're trying to get out through the column. And there's a gradient.
How's the size detected?
How you detect this?
Yeah.
So the detection of what's coming out of here, the detector is typically just like, because these are oftentimes these are biological molecules. So you might be using just a ultraviolet detection at a wavelength of 230, 280, which is just detecting typically either the peptide bond that absorbs at that wavelength, or maybe some aromatic residues on amino acids that these proteins typically might take. So it's a bulk detection of just some absorbing species, typically it's absorbers that's being used. Okay. And then ion chromatography, of course, we know a lot about that, right? That is essentially looking at the relationship of how ions, and you're doing anion exchange, because you're exchanging the anion, which is your analyte, with the stationary phase. Of course, if we wanted to separate cations, it would be the exact opposite. The stationary phase would not be ordinary ammonia into some anionic species, right? And your analyte would be cation. And the anion exchange is just being facilitated by the electrostatic interactions, the partitioning between the analyte and the stationary phase. Yeah, stationary phase. So you can look at it kind of a scheme like this and say, all right, let's kind of put it all together. I have here the exclusion kinds of chromatography where gel permeation and gel filtration are they're very similar, right? And these are separating things based on excluding things going into a space based on their size, right? So these are exclusion kinds of separation schemes versus partitioning, right? And so reverse phase, normal phase, ion exchange, those three kinds that we just talked about, are all based on partitioning of the analyte with the stationary phase functional group. Right? So it's a chemical interaction, a chemical bonding interaction, electrostatic, dipole, whatever we'll talk about that. Filtration, exclusion is not, right? It's just based on the physical size. And in fact, and this is a problem, in most size exclusion kinds of separations, sometimes there is a chemical interaction between the analyte and the matrix, the size exclusion matrix. And that's a problem, because then you can't control that, and then the relationship between size and elution time or retention time is altered because you've got some other kind of interfering effect of chemical interaction with the material. Right? And a lot of times when you start doing a size exclusion, you have to first try to demonstrate that there's no chemical interaction, like hydrophobic interactions or hydrophilic interactions between your molecules you want to separate in the matrix. So you can look at a cartoon thing like this, and so this is size, right? So you got really big things, these are molecular weight. If you've got really big things, you're not going to be doing partitioning chromatography because it just gets too complicated, because the bigger something gets, the more complex the chemical character of that molecule is, right? So when you get the really big things, you're really stuck with trying to separate those by some kind of exclusion methodology. When you have the small things, then you can start looking at partition kinds of chromatographic separations. And depending on the chemical character, whether it's nonpolar, then you might think of using some kind of reverse phase chromatography, where the stationary phase is also nonpolar. Okay? And if it's polar or ionic, highly ionic, then you do the opposite, like you guys are doing, is you probably use some kind of ion exchange chromatography. So you can have a little graph like this and say, all right, my analytes are kind of like this, and they're about this size, it looks like I should be using blah, right? And people actually do that. They use figures like this to kind of help zero in on what initial approach they should be considering. Okay, so we sort of talked about this. This is just a cartoon representation of what those interactions may look like. So if we start in normal phase here, in a normal phase, the stationary phase is what? Polar, non-polar? right there. I hadn't erased it yet. All right, it's going to be polar, right? That's what these green things are supposed to be. It's a polar functional group. And here's your molecule that has a lot of carbon and hydrogens and an oxygen, and it's going to then partition with this polar stationary phase, depending on what the chemical composition of the mobile phase is, and what this is, and what the stationary phase is, right? In reverse phase, you see now you've got a lot of, in this case, the C8. So it should be 8 of these, 1, 2, 3, 4, 5, 6, 7, 8, right? So there's a C8 column. The C8 means that you have an 8 carbon chain that's attached to this stationary bead. Okay? And of course, carbons are very hydrophobic, right? We know. And so in reverse phase, the stationary phase is nonpolar, obviously. And then we have the same molecule in the mobile phase. And you might ask, how can you separate the same kind of molecule as in this cartoon in either a nonpolar or polar stationary phase? How can you do that?
It'll just be the opposite that comes out first, right?
Well, that, yes, but it's true. That's actually important. But you do that because the composition of your mobile phase is different, right? And so sometimes people will use either normal phase or reverse phase for the same kind of molecules, but it's the composition of the mobile phase, which of course is opposite what the stationary phase is, that really helps to drive that partitioning, that selective partitioning. So here it's polar, nonpolar, relatively nonpolar mobile phase, and then the opposite for reverse phase. And now I'll talk about that in a second. Ion exchange, we're very familiar with this, right? We know this is, of course, is this an anion exchange column or a cation exchange column? What do you think it is? Anion exchange? Cation? Okay.
What goes you on?
So what's it may be hard to tell because you can't tell where these guys are supposed to be, but what's the black here is what's supposed to be the functionalized group on the stationary phase, and you see it's negative, right? And so if it's negative, that means it's attracting the opposite, and that would be these, the cations, right? And so in this case, this is a cation exchange ion chromatography because the functional groups are the opposite of the cation. Those are attracted, right? And so here, or maybe these are supposed to be mobile phase, sorry. Here's the anion, but still it's positive. And so here you have, like, in our case, you have some buffer, mobile phase buffer, that has a dissociating buffer that produces these cations that weakly associate with the anions in the stationary phase that are outcompeted for by the stronger partitioning of the anion and cation with the stationary phase, right? We just talked about. So ion pairing is a very interesting sort of deviation of some of these methods. And you'll note that in this ion pairing example, we have a stationary phase that's a reverse phase. So it's a C8 in this column example, a C8 carbon stationary phase, but we're using it to separate things that have an ionic character. And they do that because you introduce in your mobile phase is something that's called an ion pairing agent, and that varies depending on the ion on the analytes you're separating. And the ion pairing agent does this really interesting chemistry where it has this aliphatic character where it has both hydrophobic and hydrophilic character on two ends of the ion pairing agent. It hydrophobically associates with the C8 support in the stationary phase and exposes in this example, the anionic functional character of the ion pairing agent into the mobile phase space, where it can then interact with the molecules that you want. And the advantage of this kind of a thing, you might say, why do that? Why not just do this, right? And the advantage of this is that you can actually titrate by having different concentrations of the ion pairing agent in the mobile phase, and which ion pairing agent you use, you can actually titrate the degree of these ion pairing agents that associate the stationary phase that are providing the separation ability. Right? And there's lots written on that. I won't go over much more of that. Site exclusion, already talked about that, so I won't go over that anymore. Okay. Quickly, so Stationary phase deserves, reverse phase deserves a little bit more of a mention because it's probably the most commonly used chromatographic separation scheme in chromatography. And I'd say there are probably about 75%, I bet that's maybe an understatement. But if you look at HPLC separation methodologies that are published in the literature for different kinds of experiments and whatever, I bet you at least 3/4 or more, maybe 80% of them, are reporting experiments utilizing reverse phase chromatography. So it's the most widely used, and partly it's the most widely used because some of the most widely reported applications of chromatography involve high performance or high pressure, we call it liquid chromatography, HPLC, and the vast majority of those applications are in the biomedical science field. And in the biomedical science field, they're used to separate biological molecules, and biological molecules have typically varying degrees of hydrophobic character. And so reverse phase chromatography is very effective at separating biological molecules, all of which have some degree of hydrophobic character depending on the composition of the molecule. So we already talked about all this. So one thing that I want to point out is that the stationary phase typically varies, and you buy the column, it'd either be a C4 column where it's only a 8 carbon chain, or 18 carbon chain. The C18s are probably among the most commonly used. And so that's a very long carbon chain in that stationary phase that provides very strong hydrophobic character to that stationary phase for something separation. And in reverse phase, you're using this hydrophobic stationary phase in combination with a polar mobile phase. And that polar mobile phase is typically water and mixed with some degrees of a relatively polar solvent, like acetic nitrile or methanol or something like that. Right? And it's that very interesting chemistry now with water polar solvent mixtures, a mobile phase, with the nonpolar character of the stationary phase that determines what gets partitioned and separated. And I'll get to this right to the very end. In most cases of chromatography, that are using reverse phase, in general, they're utilizing what's called as a gradient elution. And that's versus an isocratic elution. And the difference between these two, in an isocratic like you're using, in an isocratic, the mobile phase is constant throughout the elution. And in a gradient elution, just like it sounds, the mobile phase changes with the elution. So if you were to look at, if I were to draw on this chromatogram, if I were to draw on this chromatogram, the composition of a mobile phase over the elution time, elution profile, if I was doing isocratic, and I'll draw it up here, isocratic would look like that. It's constant. Right? You have one reservoir filled with bicarbonate, carbonate, bicarbonate. So this is isocratic. But if I were to do a gradient elution profile, it would look something like this, where I would have one mobile phase come in here, and then I change it, and the mobile phase composition would change. By the end of the elution, it would look like this. And so this is all mobile phase A. This is all mobile phase B. So I have two reservoirs that are being mixed by these fancy pumps, and the composition of A and B is changing in a linear fashion that I program in over elution. And the advantage of that is that then you have the power to selectively elute compounds based on their partitioning with the stationary phase, in this case like a C18 column, and how that partitioning changes as the composition of the mobile phase changes. Right? So things that are weakly hydrophobic will stick to the column here. If this is water, actually this is just water. Let's say this is methanol. Okay. Things that are very weakly hydrophobic will stick to the column here, but as I start putting even a tiny bit of methanol in, they'll partition into the mobile phase and they elute out. And they come out like that. And things that are strongly hydrophobic, more strongly, relatively hydrophobic, will stay in the column. They don't like the water, they're hydrophobic, they're partitioned to the stationary phase. They stay there until the mobile phase becomes relatively nonpolar compared to water, right? And those things will elute out. there. And depending on the hydrophobic character of the analyte, it's going to elute out at different places as the mobile phase composition changes. And this is really commonly done. And so this requires you have these two pump systems, these two reservoirs, and you program in, I want to go from 100% this to 100% that over this time. Sometimes you can do this and then level off for a while to get those guys and do this, so you can program it any way you want. But by controlling the mobile phase composition in a reverse phase chromatographic separation, you have a lot of power to separate things that otherwise would not be separated.
So rather than relying on time to eventually
Well,
make everything elute out, this is just exaggerating the separation?
it's both. It's relying. So within each, it's relied a little bit on time, but within each composition, let's see. So it's relying on time, but you're looking at it like once the mobile phase character changes, then the partitioning the relative partitioning changes dramatically. That's what you're banking on. And so when the mobile phase character changes, the idea about this gradient is you're trying to say, I want things that would otherwise be partitioned in the stationary phase, that when I make this more nonpolar, they're going to now favor the mobile phase, and they'll elute out in some time frame. It's just based on the flow rate and so forth.
Is there any particular circumstance when you would do it stepwise as opposed to just like
Yes.
gradient?
Yes. Because if you have things, depending on how many things elute optimally here, based on our partitioning, is that maybe you might want to come up here, and you don't want these guys to run together like that, let's say. You come up here, hold that for 5 minutes, here, hold that for 5 minutes, there's an infinite number of possibilities. And you sort of figure that out empirically based on what your chromatogram looks like. You see some peaks running together, you change that gradient profile. Now the problem with these kinds of elutions is that these typically take 45 to 60 minutes, which is kind of a pain in the neck. It takes a long time. But if you're really interested in isolating these compounds, oftentimes when you're doing this, you're not just detecting them. You've got a fraction collector at the end of the elegant with it. You're collecting, and each time, most HPLCs have a motorized fraction collector with a wheel with a bunch of small tubes on it. It's refrigerated. And every time a peak comes up, it knows how long it takes to get from when the peak detector senses the peak to the outlet of the tubing, and it turns the wheel and it'll collect this peak, and then and another peak comes out and it turns the wheel and collects that peak for you all automatically. We walk away with all of these separated peaks, and then you go to the NMR or whatever the mass spec to figure out who they are. Right? That's what we're supposed to do.
Well, to reduce that time, can you just change the flow rate of the column?
Can you?
Yeah. I mean, if
I'm asking this as a general question, rhetorically. Can you, because in that lot, you could say, I'm just going to turn it to 5 mils a minute, I'll be out of here in 10 minutes. Right? And it's not a bad idea. People are like, but the problem is when you change the flow rate, as you'll find on this coming week, is the separation changes. The peak shapes change, and the faster you go, peaks don't get eluted as effectively, and you start running things together. And so that's all. So, if you had a chromatogram like this, you'd be like, yeah, I'm going to speed this thing up because all I got are these two peaks and they're pretty far apart. But a lot of times you'll have like that.
right. But like at the same time, if you change the gradient, you make it, let's say, like less aggressive gradient, you can still.
Yeah, that's right. And I think that is, and so we've, not lately, but we used to do a lot of HPLC of biological compounds, and it is, you could spend, and the students would spend a week trying to optimize the combination of the gradient, the composition of the gradient, the flow rate, all these things to try to get that separation, at sufficient separation in the shortest amount of time. It's very, it's kind of fun, but every iteration takes an hour. So you're like, okay, I can do this 10 times a day because I can work 10 hours. And I'm going to do it tomorrow. And so, but that's what people do. That's exactly what it takes. Is you get in there and you see what it looks like, and then you start manipulating some of these parameters empirically to look at what kind of separation. And this, of course, this profile, of course, varies from one C18 column to another. By one Dianetics column, water, they all perform slightly differently. No, it's a great, it's a lot of fun, but it's a great challenge
to actually get something to work like that. And that's how it typically goes in the real world. All right, so very quickly, these are just some examples of what these stationary phases might be in the different kinds of columns in terms of the business end of the stationary phase, right? And this is like what they're used in, whether it's normal or reverse phase, and so on. And so, whether it's just a silica, which of course is polar, highly polar, a propyl, which is not polar, and then C18, C18, and so on. For different specific applications, cyano or amino groups can be used on there that have different applications. Aromatic groups on there, more polar groups on there. So there's an enormous variety of what these stationary phase functional groups may be, and they're all specific for different kinds of applications. Right? This is what those companies do with all those people they have. And of course, all these separations, not excluding the size exclusion comment, all the ones that are relying on partitioning of the analyte with the stationary phase rely on just these simple chemical forces. Right? Now, of course, we're not talking about any covalent bonds, right? Because that'd be silly. Right? We'd never get our compound off if there was some kind of a reaction. But if we look at the relative bond energy in kcals per mole of these different kinds of bonds we've learned about, you see that when we look at ionic bonds or polar bonds that are involved in normal phase chromatography for the most part, or non-polar bonds which are involved in the reverse phase chromatography for the most part, we see that these are probably the most common for the biological molecules and even for what you're guys are doing. You see that these are relatively weak bond interactions, right? And those weak bond interactions are under standard conditions, and we manipulate that by varying the composition of the normal phase. So that we can essentially dial in those partitioning bonding interactions with the stationary phase. Okay, so reverse phase we know we need to go over this again, is looking at non-polar stationary phase, right? And looking at biological molecules for the most part. What you'd want to do is you'd want to have a sense, so that if we were to go over this in a quiz, or to ask you in a quiz, you'd be really clear on what the basis for these different kinds of exchange chromatography processes are. Right? Don't try them. And you'd know for all of them, except for this one, that they're based on competition between the analyte and the mobile phase components with the stationary phase. And it's the weak bonding interactions that are essentially establishing that partitioning strength between the analyte and the stationary phase. Okay. Now, in the real world, there's a lot more that people have done in developing columns. One really, I'll mention this quickly and I'll stop. One interesting example is how important chiral chromatographic columns are to separate compounds based on their chirality. And so they develop columns that have functional groups on them, and those functional groups are chiral molecules, and they're specific for maximizing the bonding interaction, the weak bonding interaction with analytes based on their chirality. And so where we have essentially multiple bonding interactions occurring between the analyte and the stationary phase, not just one. Okay. And one example of that is, there's many examples in the biopharmaceutical industry, but one example of that is with naproxen, which is a non-steroidal anti-inflammatory that works in the same class as ibuprofen. And so it inhibits cyclooxygenase enzymes just like ibuprofen does. And there's two enantiomers that when they synthesize this compound, there's two enantiomers that are formed, an R and an S. And this is a chromatogram of a normal separation, a non-chiral column. You can see these two forms. The problem is that only one enantiomer is biologically active, and is not. And so obviously as a pharmaceutical industry, it's to your advantage to be able to separate these two and to formulate the one that's biologically active. Which is the S band. And so they use chiral chromatography as the S band. Chiral chromatography to actually facilitate that. You can see the relative enrichment in terms of how much of this compared to that is going through a chiral column versus non-chiral column. And so when you're prescribed naproxen, as an enantiomer, it's been purified through chiral chromatography. Okay, we'll talk about that. So let's stop now. And now let's talk a little bit about the lab report. So I suspect that some of you are surprised by the kinds of comments that you got, and maybe the quantity of the comments you got in the column. The one thing I can say is that in looking across how people did is not so different than how students have done in past classes on their very first lab report. But the difference between those who did really well and those who did less well, it borders on the extent to which they really utilize materials, this is my opinion, utilize materials that we try to provide for the guidelines and the input to have you do a very specific thing. And it's not that we think it's either my way or the highway, it's that this is the format. The format that we're trying to push you and force you to use is a format that is the standard format in science writing. And so it's the format that we want you to really adopt. And at the core of that format, which is so challenging for students to learn when they're starting to do this kind of thing, at the core of that is saying things directly and concisely. There's a relationship between the number of words in a sentence and how clear the point comes across. And it's an inverse relationship, right? The more words you use, the more confusing things may be. And so you've seen comments, and we make a wide variety of comments, you've noticed in the reports. And the reports are due on Monday. The revised reports are due on Monday. And so the first iteration is worth a maximum of 20 points. And the revised report is going to be worth an additional 15 points. And so what we look for in that revision is that the net increase in quality of the report, right, and how well and thoroughly you've addressed our comments. And so some reports, many of them, the entire margin is filled with our comments. Right? And you'd be like, oh, I can attack this. And well, you start by doing it one by one. We make comments, and when we make comments, we don't make comments on a problem or something we're commenting on every time it appears. Typically, it's the first time. And we try to say, I see there's a problem here, fix this, and fix it everywhere. And so what's really important when you're looking through those comments is to don't just address a comment where it appears. Step back and think, all right, these are comments that I want to apply to the entire document, right? Even if they didn't make that comment later. Right? And when we ask you to do the revision, we're going to have you turn in the track changes, right? And it's going to be incredibly messy. In most cases, we'll be able to follow with all the track changes. In some cases, we'll have to accept those changes just so we can read it because it's been so much has been modified. But we'll be the one that makes that judgment. So you'll use track changes in Word to address all the comments and fix things. Sometimes I or a TA might make a comment that you don't agree with. And you say, I think I want to do it this way. And that's totally cool if you provide justification. You say, I'm going to do it this way, this is why.
So you want us to do the revision with the same document that you sent us back, keeping those track changes?
Yes. Okay. So you will take that document with all the comments and you'll leave them there, and that way we can see what we said before, because I don't remember. We'll see what we said, and we'll look. And one of the things I look at is to say, I have a couple pet peeves, a lot of them, but some of the ones I comment on papers is, if you have a number with a decimal, that you always need a leading zero, right? That's one thing I comment on. And I go through and say, all right, did you do that? And nothing makes me more upset and frustrated than to spend time making these comments to help people constructively improve their reports and learn from that, and then not have to do it, right? So the one advice is attend to every comment as best you can, right? Because they're meant to help improve the overall document. So the kinds of comments vary from silly little things like this, and don't put the unit right next to the number, always have a space there. These are things that if you look closely at journal articles, that would never get past the editor, the managing editor. Okay? So there's certain things that you just have, this is how it's done, and they're silly, but you might as well learn them now. And there's other things about how to word and explain things. And that's very challenging. And there's no one single case that I've ever encountered where somebody gets it like that, right? And so you'll go through this process several times, lab 1 and lab 2, and you get to lab 3. You get all this feedback. And the hope is that you're learning at each of these iterations, right? And that the overall documents, the overall process is improving, it's becoming easier. But for the writing and learning how to explain what you did and learning how to present what you did is something that takes many, many years to get proficient at, many years. So it's not something you do.
We're talking about tracking changes. Is there only something we can click on Microsoft Word that'll show up every change we made?
Yep.
There's like a setting.
Yep. So if you have not used the track changes option in Word, you have two options. Come see me or the TA, or get online and Google it. And you can, it's a nice feature. It'll follow all the changes, and you can, it marks where you made changes in the margin with a line. You can set the parameters so that it only shows what you insert. It's a different color, not what you delete. You can have it see both things. You can toggle to show the changes or accept the changes without actually accepting all of them. So you can toggle back and forth because sometimes it becomes so messy, it's hard to follow the document or reading through. So it's a very important feature that allows us to be able to see what you did in revision.
So you want us to track insertions, deletions, everything?
Well, I think that's a toggling that you can set. And so if you just did one and we wanted to see everything, we could change. We could select that. So what might be good is at 4 o'clock, if people want to come by my office, there's a room right down the hall. They have gone over your comments and stuff, and come in with the most common kind of comment is, you said you didn't like this, reword this or whatever, but I'm not sure what to do. And then we could say, this is why this is really hard for us to understand. This is why it didn't make sense, right? And a lot of those kinds of things are, the comments we're giving is, be specific. Say exactly what you did and what you mean. Don't, and a lot of times you'll say, but I think I did. And I'll be like, no, I don't quite understand, If you were to put yourself in somebody else's shoes who doesn't know anything about this lab, this is how writing needs to be, who's going to be reading this for the first time, you want them to be able to understand what you did and to be able to redo what you did, right? But you're not writing it like a recipe in a cookbook or whatever. You're writing to say, this is what I did, and somebody will be able to infer from those details about what I described how to do it and to reproduce it if they wanted to. Right? That's the balance you're trying to find.
So the second report is a full report?
For the second lab?
No, for this first lab, the revision.
Well, no. So the revision will be on what you turned in. So it's technically a data report. And so the difference between Lab 1 report, which we're calling a data report, is you have like one sentence or two for the objective, a very brief rationale, and you get into what I did. And this is how I did it, and this is my data. For the second and third lab report, you're going to have a whole abstract, an introduction with background, and then all this other stuff.
Because my understanding was that the first report is the data report, then we get it back with the revision, which will be a full report.
No. So the revision will be addressing all the comments to improve the data report.
Okay.
And improve it. Yeah. Right. So one thing that's very important for several reasons, and that is look at the guidelines that I typed up. I've spent a lot of time typing that up over the years and revising it. Look at it and follow it word by word. Okay? Cross it off word by word. Follow those guidelines, because many of you started out at a lower place than you would have been otherwise had you followed those guidelines. And so follow the guidelines very closely. Right? Look at the example lab report that we posted and that I had in the lab that may have disappeared. Right? Look at that as an example. Right? Look at the kinds of common problems that people typically have in their lab report that I would normally be talking about now, but I posted it on the website based on our experience in the past. So use those things to your advantage. And I'm sure all of you realize now that this takes a lot more time than I envisioned, right? It takes a lot of time to write. It's a painful, painful process. But out of that pain comes discovering enlightenment. That's what we're pushing to. So when you come by, if you come by at 4 o'clock today, I can look at your reports and come with some questions, and then we can go over those. Maybe we'll take some examples. If you have things you want to email me or the TAs about, it's fine to do that too, but there'll be only a certain amount of things to be communicated because I need it. So,
I'm not good with computers.
Are you guys meeting up this weekend to work on it? Are you guys gonna meet up this weekend to work on the report?
I didn't think about that, but it's a good idea.
Like tomorrow? How about tomorrow?
Maybe? Yeah,
Like in the
I'll do
afternoon?
like Sunday, or are you gonna do it tomorrow?
Oh, in the afternoon. Because Sunday I'm doing some PCAM stuff.
Okay.
It's
Why not have it?
Are you going to try to do track changes?
yeah, so any kind of document, here's a document, here's a paper we're working on, okay? So I'm in Word. I'm in Word, and I have track changes on. So if I go up to review, now it has a track changes button that I can toggle on or off, right? And now that it's on, and I can look at under this version of Word, I can hit options and hit track changes options that says, okay, track changes by color. Insertions, I'm using color only. For deletions, it's going to be stricken through. It could also be hidden or do other things, but I have strike through to show. And change lines, it does something outside border. So now when I do something, I say, oh, you didn't like this. I'll just delete this. And now it shows a cross out, and it shows a line here. If I didn't want to show the deletions, I would toggle that, and that wouldn't show, right? And when I type in something new, it shows the different color, right?
Do you want us to show the deletions and stuff?
It doesn't matter. I think it depends how messy it gets. If you're deleting a few words, but let's say, oh, you didn't like this whole thing here, and now I'm going to, take this, and I'm going to insert it up here, it starts getting hard to follow because I got to skip from here to there to there.
Yeah.
So it depends on what it looks like.
And you can adjust it yourself, right?
But you adjust it yourself. And so it's just what you toggle here. What you don't want to do is you don't want to accept the changes or anything like that because then they're permanent, right? Once you accept changes. So I could, like for all this, I could say, oh, okay, I'm good. I'm going to accept all those changes, and now they're permanent. I've lost all those edits I just made. I can't see them anymore. Right?
So you
You
want
don't do that.
You want to show those changes.
Yes, we want to see the changes because then we can say, this is what it was, this is what your revision is, and we can follow very easily what you did.
Okay. Because you have like little bubbles coming up on the side.
Sometimes
right?
you do. So you also have comments. So we have lots of comments. And we say, do this, do that.
Yes.
Those comments will stay there.
Yeah, we don't delete those.
Don't delete those.
Do we just follow the comments and
Right.
fix that?
Something will say, blah, 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 and you'll do that. There'll be some edits here that you do with track changes,
Yeah.
and that comment will say, this is what we asked you to do, and I can see you did it.
Yes.
Yeah.
Oh, yeah, you're right.
And we do that by writing track changes?
For the
Yeah, I don't
for
know
this.
what I'm doing.
Yeah, for like if you're to delete something and cross it off.
If you were to,
Saturday or
so under the review button, just by, it's off now because it's not lit up, and now it's on. And whatever, one of the options I have, what I do, how I want that to show, how I want the changes to show up. So now anything I type in, I want to, I want to have a color. That's what I do. And anything that I delete, I want to have a strike through. But sometimes I often will hit nothing to delete that they're hidden. And so when I delete something, it actually appears deleted. Now you don't see it, but I could go back and change that option, and then it will, and then I can see
That we deleted it.
that it was deleted, right?
Okay.